So today we'll continue in the preparation of haloalkanes from alkynes. So we have already seen how haloalkane is prepared from alcohols and haloalkane is prepared from alkane. Now we'll see in the hydrocarbon stage itself another thing, from how is it prepared from alkynes. So the first is addition of hydrogen halides to alkynes. So if we consider a general reaction, the alkyne is taken and made to react with hydrogen halide, then we'll get on one side hydrogen will be added and on the other side halogen will be added by breaking a single bond. So it was before a triple bond and one bond broke to make a double bond, and on one side hydrogen atom is attached and on another side halogen is attached. Again, if HX is added, now an ambiguity arises or a confusion arises that whether the hydrogen atom will be attached on this carbon or this carbon. This can be answered by again Markovnikov's rule. According to Markovnikov's rule, the negative part, in this case the halogen, will get attached to that carbon atom which is attached to less number of hydrogen atoms. So in this case, this carbon contains no hydrogen atom, this contains one hydrogen atom, so the halogen atom will be connected to that carbon atom which is connected to less number of hydrogen atom. So the halogen will be attached to this carbon and the hydrogen will get attached to this carbon. Product will be this one. So at first stage, what was formed is known as haloalkene, as there is a single halogen atom and it is an alkene. In the second stage, two halogen atoms are attached and it's an alkane, so dihaloalkane. Next is the addition of halogens. That means halogens in the molecular stage, that is X2. Alkyne, when reacts with X2, that is in molecular state of halogen, each halogen atom gets attached to one of the carbon atoms. Again, in the next step, if another X2 gets added, then again another bond will break and the halogen atom will be attached. This is a dihaloalkene and this is a tetrahaloalkane. So considering a specific reaction, we have taken propine and then added Cl2. So in the first step, this will be formed, and in the second step this will be formed, that is the tetrahaloalkane, and the previous product was the dihaloalkene. So it was the addition of halogens. Next comes a third process. So first process and second process was first the preparation of haloalkanes from alcohols, second the preparation of haloalkanes from hydrocarbons, and now the third, the preparation of haloalkanes from other haloalkanes. That is, you have to convert one haloalkane to another. Suppose it's a fluoro compound, we can convert it to chloro compound or chloro to bromo, like this. So this is known as halogen exchange process. Halogen exchange process. In most cases of halogen exchange, iodide is made to replace other halogens, because iodide acts as an excellent nucleophile to attack them and replace the original halogens. So as a general reaction, we can write RX reacts with sodium iodide to form Ri plus NaX. So this iodide goes and replaces this X, and this X goes back and combines with sodium to form Ri and NaX. Now if we consider a specific reaction, let us suppose CH3 CH2 Cl plus sodium iodide in the presence of, okay, so I forgot to mention the solvent used is acetone, and then it is refluxed. What is the meaning of refluxed? We can discuss later. CH3 CH2 Cl, it is just a process. We just need to remember that reflux is a way of doing reaction. We can discuss this later on at a later stage. So CH3 CH2 Cl, when made to react with sodium iodide in the presence of acetone and then refluxed, the iodide will come and replace the chlorine, and sodium chloride will be formed. Now this reaction's effectiveness comes from the fact that if bromide is used, suppose CH3 CH2 Br, and then made to react with sodium iodide, so here NaBr will be formed along with the product. Both this sodium bromide and sodium chloride are insoluble in acetone. NaCl, NaBr are insoluble in acetone, therefore they will precipitate out. Now as they will precipitate out, they will be removed from the reaction mixture, and we know from Le Chatelier principle that if the product is removed, the equilibrium shift towards the right, so more of this reaction will proceed towards the product side, and thus more of the product will be formed. And due to this reason, this reaction is very efficient. There is a name for this reaction when only sodium iodide is used to replace bromide or chloride. When iodide is used as a nucleophile, that is as the reagent, only then this name reaction is called Finkelstein reaction. Finkelstein reaction. Now we have used iodide to replace bromides, but we have never mentioned fluoride up till now, because sodium fluoride acts vigorously and explosively. So it cannot be controlled. As we have seen here, only one of the halogens are replaced and then an iodide is introduced, but if fluoride is used, all the hydrogens too will be replaced by fluoride, and the reaction cannot be controlled. So for this reason sodium fluoride cannot be used. So a number of other reagents are there of fluoride which is used in order to replace other halogens and substitute with fluorides. Such other reagents are namely Hg2F2, that is mercurous fluoride, AgF, silver fluoride, so mainly Hg2F2 and AgF is used, but there is also another reagent known as cobalt fluoride, but mainly these two are used. So if we use it as a specific reaction, CH3 CH2 Cl plus Hg2F2, so the fluoride compound is formed. The same reaction can also be done by silver fluoride. This reaction, when some halide is replaced by fluoride by using reagents like Hg2F2 and AgF, it is known as Schwarz reaction. This name reaction is known as Schwarz reaction. Next, so we have learned three ways of preparation of alkyl halides: one from alcohol, second from hydrocarbons, third from replacement of other halides, that is halogen exchange process. The fourth one, we can prepare halogens by from their corresponding acids or their acid salts. So preparation from silver salts of acids. The reaction is known as Borodin Hunsticker reaction, or sometimes also simply known as Hunsticker reaction. In this case, what is done is a salt is taken and it is made to react with bromine in the presence of CCl4. The product that is formed is this alkyl part joins with one of the bromine atom. A CO2 is released, that is this CO2, and the leftover Ag reacts with the leftover bromine atom. So AgBr is formed. Now the thing to notice here is in the original reactant there were 2 carbon atoms in the acid part. In the total acid salt part there were 2 carbon atoms. We broke it down and stepped down to 1 carbon atom. So this reaction can be used as step down process. Step down process is a process in which we can go down a homologous series, that is from ethane to methane, from propane to ethane, from butane to propane, that is 1 carbon down. For these reactions we can use Borodin Hunsticker reactions. Okay, so in this case it has been found that when the alkyl group, that is this part, this alkyl group, reactivity order has been found to be maximum for primary and the weakest for tertiary groups. So if the alkyl part is this, and let us consider another secondary group. So this carbon here is 2 degree, here it is 3 degree, and let us suppose a primary. This carbon here is 1 degree. So the reactivity order has been found to be this way, that is, its maximum in primary and the weakest in tertiary. Mainly Borodin-Hunsdiker reaction is done with primary salts, primary acid salts of silver. Okay, now comes the halogen part. We have not used anything other than bromine. We have specifically used bromine for Borodin-Hunsdiker reaction. This is because when chlorine is used, the yield is found to be very less than normal. So chloroalkanes are formed in a very less yield. And if we use iodine for this reaction, this reaction is a little different. That is, in the case of Borodin-Hunsdiker reaction, haloalkane is formed, but if we use iodine, a completely different product will be formed, that is, an ester will be formed. CH3 COO CH3 plus CO2 plus AgI. So as we can see, there was initially a single methyl group here, and here we can see that okay, so we need to balance this reaction. I think 2 here, CH3CO, yeah, I think that is balanced. Yeah, this one. So this should be the reaction. So one of the methyl from one molecule of CH3COAg goes and co-joins another molecule, forming an ester. So if we use iodine, haloalkanes will not be produced, but absolutely a different product, that is an ester, will be formed. This reaction is also important in its own place and is a name reaction as well. This is known as Birnbaum-Simonini reaction. Birnbaum-Simonini reaction. So this is the last stage of preparation of haloalkanes. Next we will study the methods of preparation of haloarenes or aryl halides, that is the aromatic counterparts. So this halogenation of aromatic compounds can be either done in the ring or in the side chain. So let us first write direct halogenation. Now this direct halogenation can be done in two ways. Suppose this is my molecule. If I halogenate and the product formed is this, then we call it nuclear halogenation. That is, the halogenation is done in the nucleus of the ring. Okay, and if the same reactant is taken and made to undergo halogenation and the product formed is this, then it is known as side chain halogenation. These are two different products. At first we will study nuclear halogenation. So in this case, the mechanism followed is electrophilic substitution reaction, which we have already studied in class 11. So the reaction is as follows: an aromatic ring is taken, halogen is made to react with it in the presence of an Lewis acid in the temperature range of 310 to 320 Kelvin. The product formed is an haloarene or an in this case halobenzene, and another is HX. This is because the hydrogen here has been replaced by 1X atom, and that hydrogen atom which has been replaced comes out and forms HX with another halogen atom. So this Lewis acid acts as a catalyst here, which can be easily explained by the mechanism. So let us first write a specific reaction. Plus Cl2 in the presence of the Lewis acids that are usually used are anhydrous AlCl3 or anhydrous. Anhydrous means without water, FeCl3. These are two Lewis acids that are usually used in the range of 310 to 320 Kelvin. The product formed is Cl plus HCl. So let us study the mechanism that is involved in it, that is the electrophilic substitution reaction. We have already studied in class 11. We'll summarize it as far as it is possible. Electrophilic substitution reaction. Three steps are majorly involved. The first step is generation of electrophile. So how is the electrophile generated in this case? The chlorine molecule that we have reacts with the Lewis acid in the system. As this has lone pairs, the lone pair goes and attacks, and this opens up, leading to the formation of a very unnatural product that we don't see usually, that is Cl plus, a chlorine atom with a positive charge, known as chloronium ion. This chloronium ion, being a positively charged species, loves electrons and therefore acts as the electrophile. The second step here is the formation of carbocation. So Cl plus will come and attack the aromatic ring. We know that the benzene molecule, in each of the carbon atom there is a hydrogen atom attached, so that in all I have not spotted, but in this case we need to spot this hydrogen atom while writing mechanisms. The positively charged carbon will be this one, as the bond has opened up. Now this is known as a sigma intermediate, or the carbocation. It has a special name. It's known as sigma intermediate. This is stabilized by resonance. These are the three resonance structures of the sigma intermediate, and the resonance hybrid that will be formed is so this will be the resonance hybrid. Now in the third step, the proton will be loss of proton. We can write any of the carbocation intermediate resonance structures to start with, at least. So the proton will be lost and the double bond will be formed. Who will take the proton? We know the Lewis acid has formed FeCl4 minus. This will go and take the proton and leave a double bond. So halobenzene has been formed here. These are the three steps involved in the electrophilic substitution reaction. Now, if a chloro group is already present and a second chlorine molecule is made to react in the presence of anhydrous FeCl3 in the temperature range of 310 to 320 Kelvin. Now where will this chlorine atom go? It can go here, that is in the ortho position. It can go here, known as the meta position. It can go here, known as the para position. We know that chlorine is an ortho para directing group, as we have studied in class 11, that it directs an incoming group towards the ortho and para position. So the meta will not be formed, only the ortho and the para product will be formed. Similarly, if a methyl group is present, we know that methyl group is ortho para directing. So the same thing will happen if Cl2 is added in the presence of anhydrous FeCl3 in the temperature range of 310 to 320 Kelvin. Ortho or para, actually both will be formed. We need to separate it out. For the formation of bromo compounds, it's a in this case we have used FeCl3 for making bromo compounds. We need to use Br2 and anhydrous FeBr3. In the case of iodoarenes, that is the formation of iodo compounds, it is a little difficult. For the formation of iodoarenes, if we write this reaction I2, this reaction first of all will be very reversible. That is because this is a powerful group which will reduce this back to this. So Hi is a reducing agent. It will reduce the iodobenzene formed back to benzene. So in order to remove this Hi from the reaction mixture, we use an oxidizing agent like HiO3, iodic acid. We have previously also used this technique. Whenever we see that Hi in some way or the other is preventing the reaction from happening, we remove it by using any oxidizing agent like HiO3. The reaction that takes place is we use HiO3 converting Hi back to iodine. So more amount of iodine is formed, and this reaction more is, and the equilibrium actually is shifted more towards the right. So no more prevention by Hi takes place. Now we have studied the nuclear halogenation part. The side chain halogen part will be the next part. side chain halogenation. We have already studied a little part of that, because in the last lecture we have seen that allyl and benzylic compounds readily undergo halogenation in the presence of sunlight. We will use and exploit that process here. So toluene is taken and made to react with Cl2 at 383 Kelvin in the presence of sunlight. So CH2Cl is formed, that is, one hydrogen goes away and chlorine takes its part, and HCl is formed here as a byproduct. This is not known as halobenzene, but it is known as benzyl chloride. This part is known as benzyl part. So benzyl, BNZYL chloride, benzyl chloride. But the problem with this reaction is it will not stop here. As we have seen, whenever sunlight is involved, the reaction can't be controlled. The second hydrogen atom will also be replaced. So CHCl2, HCl will be found. In the next step, we also have another hydrogen atom here that will too be replaced. At this stage there is no more hydrogen atom to replace, so it will stop here. So the problem with this reaction is it cannot be controlled. Now we need to remember this, that always the benzylic carbon containing the hydrogen atoms are replaced and not the terminal hydrogen atoms. This can be explained by an example. Let us suppose we have CH2, CH3, and it is made to react with Cl2 in the presence of sunlight, 383 Kelvin. The problem is, most of us will think that this will be formed. No, this is not formed. This carbon is the benzylic carbon, the carbon that is directly attached to the ring. The hydrogen atoms that are directly attached to the benzylic carbon, that is the carbon directly attached to the ring, will be replaced and not any other carbon. So CH2, CH3, when it reacts with Cl2 in the presence of sunlight, 383 Kelvin, the product formed is CH. One of the hydrogen atoms is replaced by chlorine and HCl is formed. This can again further react Cl2, sunlight, 383 Kelvin. The second hydrogen atom will be replaced of the benzylic carbon. So CCl2, CH3 plus HCl. In many cases, a specific reagent is used in the place of Cl2, which gives better yield, but it's not too important, but still I'll be writing it just for academic purposes. If toluene is used and SO2Cl2 is used at 475 Kelvin, sunlight is used in the presence of any peroxide, that may be hydrogen peroxide or benzyl peroxide, anything. The product formed will be CH2Cl, SO2 plus HCl. Now we need to identify this reagent. What is this? This is known as sulfuryl chloride. We need to distinguish it from SOCl2, which is known as thionyl chloride. These are different compounds and reagents. Thionyl chloride we have already used for chlorination purposes, so Just in order to differentiate, I have written the name. It is known as sulfuryl chloride, and this is known as thionyl chloride. Next is by formation of diazonium salts. So in the case of methods of preparation of aryl halides, at first we have studied direct halogenation, and this will be a halogenation by a side process known as through diazonium salts. First we'll form diazonium salt, and then after that react it appropriately to form halogens. So from diazonium salts, from diazonium salts there are many reactions through which we can do it. The first of them is Sandmeyer reaction. In Sandmeyer reaction, what is done is the diazonium salt is made to react. The diazonium salt is made to react with appropriate copper salts to form haloarenes. So the reaction is N2 plus Cl minus. This is known as diazonium salt. It is made to react with Cu2 X2 in the presence of halogen acid, leading to the formation of haloarene. And we usually don't need to write the side product, but at least the nitrogen that is released can be written. So this is known as Sandmeyer reaction. But before we study Sandmeyer reaction in a more proper state, we need to study diazonium salts first. Where are they coming from? So diazonium salts are formed from aromatic amines. These are known as aromatic amines. To be specific, this is known as aniline, but it is the class to which it belongs is aromatic amines. It is made to react with HNO2, which leads to the formation of, okay, let us write it this way because we also don't know from where HNO2 is coming. So HNO2 also is a reagent. So at first NaNO2 HCl is made to react to form HNO2 plus NaCl. This HNO2 goes on to react with aniline to form diazonium salts. In the presence of HCl at very low temperature, this reaction is done at very low temperature because otherwise diazonium salt, being very unstable, will break down. So this is the diazonium salt. This diazonium salt is made to react with copper salts to form haloarenes. So suppose we want to form chloroarene, so we'll use copper chloride. Specific reactions like this one. This is known as cuprous chloride. This is not cupric chloride but cuprous chloride because the oxidation state is 1. So chloroarene is formed and nitrogen is released. Now if we want bromoarene, this is not important whether the diazonium salt has chloro or not, only the salt is important what we are going to use. So Cu2 Br2 in the presence of HBr can be used to form bromobenzene and nitrogen is released. So these are known as Sandmeyer reaction, where copper salt is used to react with diazonium salt to form the appropriate haloarenes. But If we want to make iodoarenes and fluoroarenes, we need to use different methods. These copper salts cannot be used anymore. For the formation of iodoarenes, the diazonium salt is not used. The diazonium salt is made to react with not copper salts. Copper salts are not used anymore. Potassium iodide is used simply, and the reaction is warmed. So iodine is formed. For the formation of fluoro compounds, as it is usually very violent to use reagents containing fluorine in it, so a specific and a special reagent known as fluoroboric acid is used. This is a very important reaction, and in any way if fluorine needs to be introduced in aromatic compound, this is the only reaction that you are going to study in class 12. So N2 plus Cl minus, the diazonium salt, is made to react with fluoroboric acid. This is known as fluoroboric acid. At first an intermediate is formed which needs to be written down, otherwise the reaction scheme will be wrong. The chloride is replaced by the anion BF4 minus. As it is an intermediate, square brackets are given. Then the reaction is heated. Well, here we need to do this at a very low temperature, so 273 to 278 Kelvin, that is 0 to 5 degrees Celsius. And when the intermediate is formed, it is heated up a little bit, leading to the formation of fluoro compound, nitrogen and BF3. So this is the way how fluoro compounds are formed. There is a special reaction and it is a named reaction. The name of this reaction is Bals-Schiemann, Schiemann reaction, Bals-Schiemann reaction. So this was Sandmeyer reaction, or how we can make chloro or halo to be general haloarenes from copper salts, Sandmeyer reaction, and some special kinds also we have used. The second class of compound reaction is known as Gattermann reaction. So in the case of Gattermann reaction, it is not much different from Sandmeyer reaction at all. What we need to use is same, the diazonium salt is used, but the reagent is slightly changed. Copper is used with HCl, not the copper salt. The copper salt here is formed in situ and then it reacts immediately. So in Gattermann reaction, copper and HCl is used, leading to the formation of chloroarene. If we need bromoarene, then all we need to do is, as we said, the salt is not important here. The diazonium salts, chlorine or bromine, is not important. We can start with chloro itself, and then the reagent needs to be HBr. So the bromoarene will be formed. Okay, these are from diazonium salts we can produce. Third class is the silver salt. From silver salts, as we have studied already, Hunziker reactions. In the case of aliphatic, we have done Hunziker reaction. Now we are going to use that same thing in aromatic compounds. From silver salts of aromatic acids, also known as Hunziker reaction. What we do here is we take the appropriate aromatic compound, its acid salt plus Br2. In the presence of CCl4 we reflux it, and this whole part gets removed and Br comes here, plus CO2 plus AgBr. So the appropriate haloarene is formed. Now the last part, the last reaction, that is the Raschig process, which is used as the commercial process for the preparation of chlorobenzene, the Raschig process or commercial preparation of chlorobenzene. This is how it is made in industry. So the mechanism is not important here. C6H6 2HCl in the presence of oxygen, and the catalyst used is copper salt, that is cupric chloride, and heat is given to form 2C6H5Cl, that is chlorobenzene plus 2H2. This is the industrial way of preparation of chlorobenzene. We will stop this lecture here, and in the second lecture we will start from physical properties of haloalkanes and haloarenes and how their reactions that are given by it.